Okay, welcome back everyone to another algebraic graph theory seminar. This week we have Sjanne Zeijlemaker, who is going to be telling us about optimization of eigenvalue bounds for the independent synchromatic number of graph powers. I'll let her take it away.
Yes, thank you. So as you can see, this talk will be about the optimization of eigenvalue bounds for the independent and chromatic number of graph powers. This is actually my first work as a PhD, so I'm very happy to share it with you here. And this is a joint work with Aida Abiat, Gabriel Coutinho, Miguel Angel Fiol, and Bruno Nogueira. So this talk will be divided into several parts. So we just start with some background on the problem and some history of spectral bounds. And then we will look at two different categories of bounds. So first we look at a specific case where the spectrum of the power of a graph is related to the spectrum of the graph itself. And then we present and optimize some bounds for the general case where this is not the situation. So as the title suggests, what will be very important in this talk is the spectrum of a graph. And we will have two different notations for this depending on the context. So we will use lambdas in non-increasing order when we mean each and every single eigenvalue. So for example, as you see here for our all-time favorite graph, the Peterson graph. But we also use theta sometimes when we specifically mean distinct eigenvalues. So in that case, we put a superscript for the multiplicity. And we want to relate these eigenvalues to two NP-hard parameters of graphs. So one of them is the independence number. How many vertices can we pick such as none of them are neighbors? For example, in this graph, it's very easy to convince yourself that indeed we can pick 5 of these orange vertices. And that is as large of an independent set as we can find here. But we're also interested in the chromatic number. So if we color every vertex such that no neighbors receive the same color, what's the minimum number of colors that we need here? And specifically, we want to consider these parameters for a specific type of graph. So we say that the kth power of a graph, which we denote by g to the power k, is the graph where we have edges for every pair of vertices where their distance was at most k in the original graph. So for ks1, if we start with the cycle, then for ks2, we get these extra edges here between vertices at distance 2, same for distance 3, etc. And here you can see that the diameter is 4. So if we just keep going like this, we eventually end up with the complete graph. And in a similar way, we can generalize the independence number. So the k-independence number is the maximum size of a vertex set where their pairwise distance is greater than k. So k is 1, that just means that they're not allowed to be neighbors. So that's the normal independence number. But for k is 2, for example, in this 8 cycle, we can only find a maximum set of size 2. And an easier way to think about is that the k-independence number is really just the independence number of this kth graph power. So as you can see here, indeed, if you draw the extra lines, then all these black vertices are connected to an orange one somehow. So the set is really maximal. And the same thing holds for the chromatic number. So the k-chromatic number is really just the chromatic number of this kth graph power. So rather than chromatic number 2 for a cycle, we see here that we now require at least 4 colors for ks2. Now we can relate these two quantities to a well-known inequality, which is given here. So the chromatic number is at least the number of vertices divided by the independence number. And if we replace g with g to the power k, we see that indeed this also holds for alpha k and for phi k. So sometimes in this talk, we will switch between these two parameters, and then this is really what we're applying in the background. And our goal today is to extend and optimize certain eigenvalue bounds for the independence number to hold for this k-independence number. And by this previous slide, that also will give us lower bounds for the k-chromatic number. Now, our motivation consists of two different parts. So first of all, computing these things directly is NP complete. And it was actually shown even for very specific types of graphs that the problem remains NP complete. So we don't really have the feeling that this should be easy for many types of graphs. But eigenvalues can be computed in polynomial time. So these are very good candidates to upper bound these kind of quantities. And secondly, so based on my previous slides, you might already wonder, well, if the k-independence number is just the independence number of this graph power, can we just take a bound on the independence number and apply it to g to the k? And well, essentially this would give an upper bound on the k-independence number. There's one particular issue with this. Because we know nothing about the spectrum of this kth power given just the original graph. So in a general situation, there's no relation between these two. And what we want, therefore, is to have a bound that really only depends on the graph that we are given originally. So this k-independence number is relevant for several applications. One of them is, for example, in coding theory, where we can see a code as a k-independent set in a Hamming graph. So in this case, if we have a code which is too independent, then you can see that this parameter k relates to its error correcting capability. So if we have one bit flip, we can just round to the nearest neighbor and still get the valid code word back. And another application is the quantum independence number, alpha q. So in the same way as the normal independence number, you can generalize this to k independence. And for this parameter, we don't know whether it is in general a computable function. So here to have some kind of upper bound is even more valuable. And some of the bounds that we present in this paper and in this talk also upper bound the quantum k independence number. And finally, we can relate this to several other graph parameters. So an example of this is, for example, the average distance. And we can use this k independence number to lower bound it. Now, the main tool for proving such eigenvalue bounds will be interlacing. Given a sequence of lambdas and a shorter sequence of mu's, we say that these two interlace if these inequalities hold for every index. So to put it visually, if for every mu we have these two lambdas where it's sandwiched in between. The name interlacing, I guess, makes more sense in the most extreme case. So if we have m is n-1, we see that we can just alternate between these two sequences and we have a non-increasing order. Now in our case, we want to relate this to graphs. So a sequence will be a sequence of eigenvalues of the adjacency matrix. And in that case, we have two situations where we know that interlacing always occurs. So one of them is called Cauchy interlacing. And this is if we have a principal submatrix of A. So in graph terms, if we take an induced subgraph, then its eigenvalues interlace those of the original graph. And the same happens for a quotient matrix of a partition. So if we take the matrix where every cell is the row sum of a part of this partition. So then again, we have this interlacing. And now using these and some other techniques, several bounds have already popped up in the literature. And actually most of the work in this area is based on two classical bounds. So one of them is the inertia bound by Cvetkovic. And it basically states that the independence number is upper bounded by the number of non-negative and the number of non-positive eigenvalues of the graph. Or if using this inequality, we reformulate it for the chromatic number, we get the following. And for regular graph, we also have a second bound. So this is called the ratio bound, and it's an unpublished result from Hofmann. And if the graph is regular, then this expression here is an upper bound for the independence number. And this bound also comes with a necessary condition for equality. Now this bound is related to some other number of a graph that you might have seen before, the Lovász theta number. And this bound is a lower bound for the Hofmann bound. So it's basically in between alpha and lower than the Hofmann bound. Now, the reason that this ratio bound is still very much used is that it's much easier to compute, as you can see. So this low-pass theta number actually requires some semi-definite programming, where here we just fill in some numbers. And there's also some applications that follow directly from this bound. So for example, the Eros-Colorado theorem. I think we've actually seen this before a few seminars ago. Is a famous theorem that states that if we have some subsets of a larger collection such that any of them intersect, then we have an upper bound on the size of this collection. And using the ratio bounds, we can also prove this with graphs. So a Kneser graph is a graph where the vertex sets are subsets of some larger sets and the edges are defined by void intersection. And we can restate this, therefore, as Eros-Colorado theorem. So we're essentially looking for the largest independent sets of this Kneser graph. So if we apply the Hofmann bounds to the graph with its eigenvalues, you see that exactly this Eros-Colorado theorem will come out. So even these simple versions already have many applications, but then it's also been generalized in many ways to the k-independence number. So I listed several results here. I'm not going to go through all of them, but an important one for us here is this one by Viel. So this was the first eigenvalue upper bound on this k-independence number. And you also see some results here for more specific types of graphs. So for example, a tied upper bound for the two independence number of a tree. But today in this talk, we're more going to consider the general case. So we don't want to put too many restrictions on our graphs. Now, this idea of applying optimization to spectral bounds is not entirely new. So I mentioned before this low-pass theta number, which is semi-definite programming. But there's also something called the Del-Sart linear programming bound. So this only holds for a particular type of graph, but it's linear programming, so it is a very efficient bound. And actually, this was found in relation to some coding theory problem. So it was only found much later that this also upper bounds alpha. And then recently, Viel came up with some generalization of the ratio bounds, which he could translate to a linear program to solve for specific types of graphs. So this resulted in something called the minor polynomials. So part of our motivation here as well to take the inertia bounds, so the second classical bound, and see if we can find some linear programming counterpart for this version. So this paper is part of a trilogy. We had in 2016 some new bounds on alpha k. And these bounds would always contain some term of an eigenvalue to the power k. So this raised the question, can we maybe generalize this? So can we replace this with some degree k polynomial? And actually this turns out to be the case. So now we have this bound with degree k polynomial in it, which we are basically free to choose. And of course, the next natural question was, well, how do we choose it to get a good bound for specific graph types? So the idea of this latest paper and also of this talk is to optimize these bounds for specific graphs. And before we do this, I would like to start with a more nicer situation. So in certain cases, the spectrum of a graph power is actually related to the spectrum of the graph itself. And part of this is inspired by some question from Alon and Mohar. So they asked, if we fix the maximum degree and the minimum girth of a graph, what's the largest possible chromatic number of the kth graph power that we can achieve? Now for KS1, this question was already asked before by Weising, but even then it's an interesting question. So if we allow triangles, the question basically becomes trivial. We just pick the complete graph. But otherwise it is not. So even for KS1, this already sparked a lot of research into triangle-free graphs. And for larger k, the question became even harder. So k2 was already a long-standing problem from Ising. This was already settled using the probabilistic method. And the case k2 was also settled asymptotically. But for at least 3, basically the question is still open, and we only have some lower bounds. So with this question in mind, we looked at a specific type of polynomial related to eigenvalues. So if we're given a graph with a spectrum of thetas, and we consider this inner product, then we say that the predistance polynomials are the polynomials which are orthogonal with respect to this product, and where their index denotes the degree. And we normalize them based on the largest eigenvalues, such that these are unique. And Friol in 2012 came up with some upper bounds on the sum of these polynomials, evaluated on the largest eigenvalue. So this lemma is what we will be using for our bounds. And the important part is that we have an if and only if condition for equality. And as you can see, we have equality if the adjacency matrix of G to the K is some polynomial in the original matrix. So essentially, we can apply this whenever the spectrum, well, not whenever, but in a case where the spectrum is related. So that of G in the spectrum of G to the power K. And if we combine this with these two classical bounds that we saw, then we get the following two lower bounds for the k-chromatic number, as long as the graph is regular. So we see that this first one resembles the Svetkovich bounds, where now there is this polynomial q involved, and the second one looks a lot like the Hoffman bound. Now there's one particular case when we always have equality in this lemma, and this is when we have a regular graph and we choose k in terms of the girth. So the girth minus 1 divided by 2. And in that case, the graph is k partially distance regular. So what this means in particular is that these predistance polynomials are easier to compute. We could just solve this recursive function. So that also means that our bound is much easier to compute and apply. And this is what we also did for several named graphs in Sage. So here you see the graphs for which our bound was actually tight and also not completely trivial. Now, to keep things a bit more uniform in this talk, we usually translate all these tables back to alpha k so that you can sort of see the relation between these different bounds. And as you can see, these graphs don't all have a very large girth, but there's also one for which for k is 3, we still get a tight bound. And other examples follow from some paper by Kang and Pirot. So this is a paper in relation to this question that I showed. And they introduced something called a balanced bipartite product. So they take the Cartesian product of these parts of the bipartition and they connect these in some way. And their construction is actually very elaborate, but even if we try this for quite simple graphs, like certain even cycles, we also find something that gives equality for our bound. So we can see that paper with a very different outlook on this question actually provides examples that also work very well for our spectral bounds. Now, in general, we don't have any type of relation between the spectrum of a graph power and the graph itself. So in that case, we need to do a little bit more work. Given a graph with its adjacency matrix A and some polynomial p of degree k, we say that W of p is the minimum entry of the matrix PA. So of the matrix of this polynomial evaluated on the adjacency matrix. And big W of p is the maximum diagonal entry. And in that case, we can formulate an inertial type bound, which looks as follows. So it's very close to the Svetkovich bound, but instead of just counting non-negative and non-positive eigenvalues, we have this polynomial p on either side. And now just to give you an idea of how to prove these type of bounds, I want to give a very quick proof sketch of this one. So suppose we have a maximum k independent set with size alpha k. Now by just permuting the vertices, we may always assume it's in the top left corner here of this matrix PA. And we know what this block must look like. So it's k independent, so it has no walks of length k between either of the vertices. So that means it only has potentially some non-zero entries on the diagonal. And if we say that mu is the smallest eigenvalue of this submatrix, we can derive two things about it. So first of all, we have a principal submatrix here. So we can apply Cauchy interlacing. And we find that at least the size of this set, so at least alpha k eigenvalues must be larger than this eigenvalue mu. But at the same time, by definition, since these eigenvalues are on the diagonal, we also know that they are at least p. So if we put that together, we see that we get this first term of this bound that we saw. And in a very similar fashion, we can also obtain the second one. Now, before we start with any type of linear optimization, a very valid question to ask is this linear? And we can see this more easily if we apply some transformations to it. So first of all, we can just assume that only this first term of the minimum is here. Otherwise, if we take the polynomial minus p and translate a bit, we can just obtain the second term. And we may also translate it such that w is 0. So then we are left with this expression here, which is slightly simpler. And we can translate this to a mixed integer linear program. So the input of this program is the distinct eigenvalues with their multiplicities. So the input size depends on how many different eigenvalues there are. And the way we solve this is for every vertex, we assume that it is this smallest, corresponds to the smallest diagonal entry. So we said that we could shift this entry to be 0, and then all the other entries on the diagonal have to be at least as large. And we have this characteristic vector b, which encodes with a 1 and a 0 whether this polynomial evaluates to a non-negative number on an eigenvalue. So we have a 1 exactly if and only if our bound holds in this case. So with this mixed integer program, we can compute the bound for several graphs. Now, for large graphs, this takes quite a bit of time, as we have to solve it both for every vertex and its mixed integer programming. However, we don't have any kind of regularity requirements. So compared to this previous bound from Friel, we have quite an advantage here. And even if we look at, for example, small irregular graphs, we already see that for quite a large percentage, we still find an optimal solution which corresponds to exactly to the value of alpha. Now, if we look at the named graphs in stage again, we can compare it to some of the previous bounds. So this is, the first column is this bound from Friel, and the second one is the Lovász theta number. Now, as you can see, we are generally a little bit outperformed by this first bound. However, there's also some irregular graphs in this table. So there are several entries for which we can now find an upper bound which we could not find previously. And actually, if we add an extra assumption, we can also bring down this running time considerably. So if we assume k partial walk regularity, so basically for any number smaller than k, a vertex is always contained in the same number of closed walks, then we have a constant diagonal of P of A. So basically what this means is that these two conditions can now be summarized by just setting this diagonal to 0. And we only have to solve one mixed integer programming now. And this condition is the same condition as this ratio type bound. So we're now working in the same setting. Now, one graph for a family for which this works well are the prism graphs. So these are Cayley graphs of the dihedral group, and these are walk regular for any type of K. And as long as n is not equal to 2 mod 4, we see that our program gives a tight answer. So we always find exactly the value for alpha 2. And another infinite family for which this works very well are the odd graphs. So there's one odd graph that we all know, it's the Peterson graph, and it's basically defined as where the vertices are some subsets of a larger set, and edges are defined by void intersection. So for this graph, we know the eigenvalues and the multiplicities. And if we look at our mixed integer program, we see that for the odd graph OL, the L-2 independence number will always look like, will be upper bounded by this. So this mixed integer program, we always give to L-2 for odd L and to L-1 for even L. So to just give you an idea of why this is the case, so if we're in the odd situation, then we have L-2 roots of our polynomial, also an odd number. So really the most efficient thing we can do here is place these in such a way that every single eigenvalue evaluates to a negative number except possibly the first one. So we get that the multiplicity of M1 is exactly the upper bound for the L-2 independence number. And if we're in the even case, then the best we can do is the same, but we will have these two extreme eigenvalues exposed. So in that case, M0 plus M1 will be an upper bound. And for all the small odd graphs that we can test this for, with the exception of O5, we see that this is indeed a tight upper bound for the K independence number. Now this bound that we have generalized here for KS1 can actually be strengthened. So Elphick and Bocquian showed in 2017 that the following expression is also a valid lower bound. So what they did here is specifically consider the case when an eigenvalue is 0, rather than just looking at non-negative and non-positive. And if a graph has no 0 eigenvalues, you see that this term will vanish, and we just have the Svetkovich bound. But when we do have eigenvalue 0, we get a slight improvement. So the idea is also that if we manage to generalize this, that perhaps for graphs with eigenvalue 0, we can get an improvement for the K independence number. And it is actually possible to generalize this bound. So again, we need K partial walk regularity. And we also need the extra condition that this degree K polynomial sums to 0 on the eigenvalues. But if we have both of these things, we can basically follow the same proof as from the original bound. And we get a very similar type of expression, again with this polynomial involved. And also in this case, we will only just take the first term of this maximum. So if we just take minus p, we can flip the signs and obtain the other one. In a similar way as before, we can translate this to a mixed integer linear programming. So summing to 0 on the eigenvalues is a very straightforward condition. But now to compute the bound that we want, we have to keep track of several things. So we have a characteristic vector for when p evaluates to a non-negative number on an eigenvalue, and also for strictly positive. So together that is enough to compute everything. And to linearize our bounds, we fix the number of eigenvalues where p is positive. So for 1 up to n-1, we will again solve a separate mixed integer program. And by doing so, you see that this objective function is now linear, and it expresses exactly what we wanted to compute. So in theory, this all works very nicely, but we ran into some problems with the practical application. And the main issue here is that really no solver has infinite precision. So if we just look at a graph that we saw before, some prism graph, gamma 4, we can easily check that its 2 chromatic number should be 4. So if you pick one of these green vertices, for example, the only other vertex at distance 2 is more than 2 is really the other green one. So this is an optimal coloring. However, if we look at what our mixed integer linear program will give us, for example, if we solve it with Kurobe or its stage, we get some optimal polynomial with a root in eigenvalue 3, and another root just before this other eigenvalue -1. So if we compute the bound, that actually gives us a lower bound of 7, which of course makes no sense because the actual answer is 4. So what we run into here is some rounding issues. So this polynomial doesn't exactly sum to 0 on the eigenvalues. So it shifts slightly to the left here. And if we do the computation by hand, we find that this is actually the optimal polynomial that we want to find with this bound. And this gives a tight answer. So we've tried to solve this with some reformulations and many epsilons. And in the end, we also just restricted ourselves to a simpler case where we could really just make sure that none of these errors would happen. So if we have a regular graph and we consider k as 2, then a polynomial of this form will always sum to 0 over the eigenvalues, as you can easily check. And this is independent of this coefficient b that we have here. So what we can do is restrict ourselves to this shape of polynomial and start optimizing over this coefficient b. So to do this, we no longer need to solve a mixed integer programming. So essentially, we're no longer dependent on a solver, and we can much easily control what is happening here. So the strategy is actually greedy. Supposing some eigenvalue is the smallest one where this polynomial is negative. Now, in that case, it is always beneficial to place the negative root as close to this eigenvalue as possible. So you can see as you do this, then the positive root will also shift to the right. So there's potentially more eigenvalues where p will be negative. So we can just look over all the eigenvalues and check this. And there's several edge cases that we need to keep in mind. So minus p is also a valid polynomial in this case. So in that case, it's kind of mirrored where we want the root to be slightly to the right, of the eigenvalue. And it could also be the case that, for example, all eigenvalues that are negative evaluate to some positive or negative number. So perhaps we have to also place the root next to 0. And the case where things previously went wrong is if perhaps one of the eigenvalues is exactly a root of the polynomial, or in this case, both of them. So in this more controlled setting, we can actually check more closely for rounding errors and ensure that we actually get the correct result. Now, even though we are restricting ourselves quite a bit, we can see that for this second mixed integer program, we already get much better results than for the first one. So in particular for these graphs that I highlighted here, so the Gaussian graph and the Klein-7 regular graph, we get an improvement of 6. And for example, this Klein-7 regular graph has eigenvalue 0 with a large multiplicity. So we indeed see that this case where we were hoping to get an improvement actually works in certain cases. Now there's another graph for this, which this works well. So again, these prism graphs that we saw before. But now we also get the incidence graphs of certain projective planes as side examples. So again, we have an infinite family for which this bound is tight. Now, apart from this optimization, we also looked at a different type of bounds, the ratio type bounds. And we also came up with 2 results here. Now, these results are not very suitable for optimization, so we have not managed to do this yet. But I just want to show you quickly what we found here. So the first ratio type bound is a generalization of a previous result of my co-authors. So if we have a regular graph and some degree k polynomial for which its minimum is not on the largest eigenvalue over all the spectrum, then this expression here is a lower bound for the k-chromatic number. But actually, if we follow the proof of the Hofmann type bounds from Hammers, we can show that this regularity condition is not strictly necessary. So even if we have any type of arbitrary graph, we may always apply this bound to find the lower bound of the k-chromatic number. And a second bound can be derived under the same circumstances as this second inertia bound. So if we have k partial log regularity again, and some degree k polynomial which sums to 0 on the eigenvalues, then we can also get a bound in terms of the eigenvalues of this matrix P of A. So if this second eigenvalue of this matrix is still strictly positive, we get an implicit expression for Hk. So we see in this case, it appears in two places. So you can imagine that optimization in this case is not really doable, but it's still a good bound to check theoretically whether certain values of Hk are possible. And again, the proof is very similar to that of the original ratio bound. So what we're essentially doing is interlacing with a specific type of quotient matrix. Okay, so I've shown you many types of different bounds today. So I think it would be good to close off with some applications and ideas that we would like to investigate regarding these bounds. So as you saw, we tested them for several graphs in Sage. But it would be interesting to, in particular, look at different values of k, and also try and apply this to other graph families. And we're especially interested in the case where this del start LP bound is not applicable. So this bound has two very nice characteristics. It's efficient to compute, and it's also quite good. So we really don't want to compete with this. But it has as a downside that it's very restrictive. So it only holds for a particular type of graph. So we hope that in the area where this bound is not applicable, that we can still get some improvements. And actually, as we were testing these different types of graphs, we found something interesting for the odd graphs. So for these graphs, our mixed integer linear program outputs polynomials that converge towards the minor polynomials. So these are the polynomials that Viol used in his optimization of the ratio bound. And this is interesting because these bounds are in general believed to be incomparable. So if there's really some kind of relation here, that would be interesting to investigate. So it would be nice to see if this is some lucky coincidence, or if through this mixed integer program, we can perhaps bring these bounds together. Some application that I mentioned before is in coding theory. So using bounds for alpha k, we can show that certain types of perfect codes cannot exist. So whenever we have some improvements for this k-independence number, we can also check whether that leads to an improvement in the area of coding theory. And finally, it would be good to see if these mixed integer programs can perhaps be refined in some way. So the ones that you saw, they all work, but they are all not necessarily optimized to, for example, exploit symmetry and other techniques. So it would be nice to see if we can speed them up in some way to make them applicable to larger graphs. So yeah, that's all I wanted to talk about today. Thank you all very much for coming. Are there any questions?
Thanks. Thanks so much. Yes, indeed. Are there any questions? So I can start with a clarification question.
Okay.
I think it's something you mentioned, but I was having internet issues near the start of your talk. So I apologize if this is repeat for everyone. But did you explain why the kth power graphs are sort of so susceptible to this sort of analysis, or why you can improve these bounds, or why you can sort of port these bounds over for them?
So I'm not sure I mentioned this. I'm just going to race back to the beginning. But in a way, it's a very natural generalization of the independence number. So normally you're essentially checking for k is 1. So you want things to be further apart than 1. So in that way, it's natural to generalize to a larger distance. And one of the reasons we're just interested in this is that, for example, in coding theory and in relation to these other graph parameters, this parameter specifically also seems to make sense. But yeah, you could probably come up with some different kind of graph structure for which you could bound the independence number. So if you look at the second paper that I mentioned in this line of work, you can actually see that there's 3 different generalizations of the independence number, and they all seem to make sense somehow.
Right.
So it's just that this one is easy to use for upper bounding.
Yeah, and so I guess the question that raises for me is what kind of, you mentioned at the end you want to apply this to other families. Do you have ideas of what other families might go nicely with this?
Yeah, so that is sort of the question that we also have, because so for this del start bound, it was shown specifically that it holds for distance regular graph. But if we look at the proof, that doesn't necessarily seem to be if and only if. So we're looking into the case where whether whether graphs that are not distance regular, whether they're also applicable to this bound or not. So specifically, a lot of these bounds we have hold for walk regular graphs. And some of these are not distance regular and probably do not work for this del start bound, but for some reason, it doesn't always generalize the way you want to. So for example, these odd graphs work very well. And then we looked at twisted odd graphs, thinking that would be the same. And the bounds were not just bad, but just absolutely horrible. So it's very hard to get an intuition of what we should test to get good results here. But I mean, if you have any suggestions, that would be very welcome, because we've tried many things.
Yeah. Certainly not off the top of my head, but it's an interesting question.